Today, we are going to start talking about a very important subject, compositional data analysis, which in my opinion should be a subject that should be taught at every university in the world, especially for geologists. And I will begin today showing you an introductory presentation of the subject. And on the next episode, I will show you step by step how to process compositional data analysis using a free software known CoDaPack that can be downloaded from the internet. All the reference will be in the comments and in the video. So let's go now and see this presentation that was originally intended for Discoveries 2019 in Mexico. Good afternoon and welcome to this presentation. Thank you to Discoveries Mining 2019 to allow me to use this means to do the presentation. I'm sorry I cannot be there with you guys. To obtain a copy of this presentation, including a video explaining each slide, please write me an email at vallsvg@gmail.com. My story with compositional data analysis started in 2004 when on the last day of the 32nd International Geological Congress, I was passing by a room and I saw a sign saying compositional data analysis. Sounded very interesting. I entered and started talking to the people, and as a result, they invited me to their biannual conference, CoDaWork 2005. And during a break, I remember everybody was happy talking about compositional closed system, ALR, ELR, permutation. And I said, guys, what about correlations? And there was a silence. And it was like I was yelling pork in the National Assembly of Vegetarians. So one of these guys look at me and say, correlations? That doesn't exist. Correlation is an illusion. I say, who said that? And they say, well, this guy, Carl Pearson, who invented the correlation analysis. And this is really interesting that the guy that wrote and discovered the method advised that there were problems when you were trying to apply correlation to closed system. A closed system is a system where the data has been estimated on the basis of something, let's say part per millions or part per billion percentage. So I say, what? That means that I have been working statistic wrong all the time? And they say, yes, you were. Basically, you cannot do correlation analysis on closed data like your chemical data. If I was another type of person, I will say, okay, you're right, and this will be the shortest presentation on Discoveries 2019. But being a Cuban and very stubborn, I said, no, this cannot be like that. I've been using correlation all my life. So I decided to test their statistic and my statistics. So I created a model. Copper mineralization in a porphyritic environment where the original paper can be downloaded from a Wikipedia. There is a link at the bottom of the slide. So this is how the data looks like. It has not only major element, but also trace elements. And the initial data had three conditions. The first one, it was a closed system, meaning that when you sum all the values, you get 100% or close to 100%. There are no zero values present or below the detection limit, just to make this simpler. And there are no statistical outliers or hurricane values present. Okay. There were also embedded positive significant correlation between certain elements like copper, arsenicum, nickel, and cobalt, as well as negative significant correlation between other elements like potassium, calcium, silica, aluminum, etc. So according to this embedded condition, any correlation analysis should give me these two set of coefficients: silica versus aluminum, or calcium, sodium, copper, arsenic versus magnesium, potassium, nickel, and cobalt. So I start by processing the whole data set. Since we don't have zero values or not statistical analysis, the process was very simple. We determined the distribution law. If we got a log normal distribution, we converted to the logarithmic version. We use Excel to calculate the Pearson correlation, and the critical value of a student was used to determine which of these correlations were significant. So you have here a case of an example of the table of correlation. You notice, for example, in the first column, you have negative correlation between silica and aluminum. That's one thing that we wanted. We put those correlations there. So they're there. So when making my range correlation coefficient, I'm sorry I cannot be there to explain you in detail how do we get this coefficient, but basically any element that is next to another one, they are directly correlated. Any element that is on top of the other one are inverse correlated. So in this case, for example, aluminum is directly correlated to iron, but aluminum is inversely correlated to silica. Okay, so these were the two correlations that I got. If you look at this in detail, you can see my original correlation are there, but there are also a lot of what is called spurious correlations that they don't exist, but mathematically we got them. One of the best examples is the silica titanium, as you can see here in the graphic, is not existent. So when I try to make the map of the RCC1, this is what I got. And let me get the laser pointer. So if I was a geochemist and I send this map to my boss and I say, well, we need to drill, you're probably going to be drilling here, here, well, here too, here, here. Maybe you will go out of your here. So of the 4 holes that you will be probably drilling, only 1 or 2 will be close to the anomaly. So that's the current situation. That is why you use correlation and you get some results, okay? Because you get some, but you don't get the full picture. And this was our best RCC. Okay, not very good. But I said to myself, well, maybe because I'm mixing the major elements with the trace elements. So let's separate them. Okay? And no cigar. We got almost the same result, just better structure. Okay, in this case, we probably will be drilling here, but we also will be drilling here and we'll be drilling here. So it's like a 1 in 3 cases to get the actual anomaly. So yes, regrettably, it is clear that closed system provokes spurious correlation. And it's especially true when you're trying to combine major oxide with trace elements. So a better solution will be to separate those group majors from oxide, but there are clear disadvantages of doing that. Okay, so my statistics is not good enough. What about theirs? Because, okay, I'm very stubborn. So as I mentioned, CoDaPack uses 3 algorithms, ILR, CLR, and ILR, to transform your data from a closed system to an open system. This is an example of using one of the algorithms, the CLR, and as you can see, the sum now of all the elements is 0, not 100. Once you convert the data to an open system, you can come back and use your normal Excel or SysStat, etc. CoDaPack allows you to do a statistic within the simplex, within the CoDaPack system. But you can, go back and use your normal Excel. So this is the coefficient that I obtained. And here is how we look in the map. As you can see, a much better result. First of all, the structure is much better, and we are concentrating right in the mineralized zone. So this map is really good. Now, if we only use the strongest correlation, like above 0.95, then we get these two coefficients, and the map is almost a perfect, correspond almost perfectly with the ore body. That is very good. Now, as I mentioned, they have other algorithms, the ALR and the ILR. The ILR, that's the coefficient, that's the map. Again, almost a perfect match. And the ILR, which is the best, a little bit more complex, that is your result. As you can see, you are really, really concentrating on the center of the anomaly. So, some conclusion of their statistics is we get rid of the spurious correlation. The correlation we have are the real ones. We can process the whole data, measures and trace elements together, not a problem. There is no need for testing for statistical outliers or distribution loss. And one of the most important ones, you can now believe in your chemical maps, which is something very, very useful and important. Now, wait a second. There are other statistical methods like FAR assay or, well, sorry, factor analysis or principal component analysis. So how do they do? I apply factor analysis to the raw data and to the IRL transform data, and we get maps. As you can see, factor analysis works very well too. But the problem with factor analysis is that you need to know what each factor represents. So it requires a much better understanding of the geology, or a test this, and see which one gives you a better result. Again, the factor analysis applied to ILR gave a much better distribution of the anomaly. So if you want to keep using your old way of processing, your old system, please use only the strongest correlation. That way, at least you're going to minimize the chance of having a spurious correlation within your data. And do not mix trace element with major oxides, because that doesn't help. Of course, factor analysis is a very good method when you can use them combined with your brain. But if you really want to get all the information from your data, make sure that there are no spurious correlation. Not worry about distribution law or statistical outliers. Then welcome to the CoDa family. Thank you for your attention. As I mentioned before, the original paper can be consulted and edited at Wikibooks. That's the link there. And I also want to mention, since I'm here, this book is called Exploring Geological Data with WECA, CoDaPack, and Insight, which is a step-by-step graphical guide, not only of how to use compositional data analysis, but also how to use artificial intelligence in the processing of your data.
I will be talking in this episode again about compositional data analysis. I will be showing you how I use the program CoDaPack, and we will work on a real example. Again, I will recommend you to get my book, Exploring Geological Data with WECA, CoDaPack, and Insight. I will put a link in the description to Amazon.com, where you can buy the book, or the Kindle edition. It is an illustrated step-by-step guide, not only how to use CoDaPack, but also how to use WECA, that is artificial intelligence, and Insight, different way of graphically presenting your data. So for this webinar, we will be using our old dataset. And again, you can download the dataset from Mendeley. I will include also a link for the site. So let's go and check our data. We are back at our dataset. Before we can process our data with CoDaPack, we need to do some steps to prepare the table in order for CoDaPack to work. The most important addition is that we need to add here a new column, which are called the other, which is the result of this equation here, where we sum all the values of the trace elements and subtract that from 100%, which is the total amount of samples. So this is a very important step that we need to do, and this is the formula, because we're working on part per million. So if you have this in percentage, it will be 100 minus the sum of all these elements here. The second step is to organize the elements in accordance to the method that we're going to be using for interpreting the data. I usually arrange or group the elements in accordance to their genetical origin. And for that, we will be using these tables here. I put it here so you can consult it. All these elements are characteristic of precious metals. All these elements are characteristic of base metals, base metal with chalcophile indicators, high field strength elements, rare earth, platinum group, lithophilic, and major. So using this table, we organize the elements. For example, molybdenum and gold and vanadium. These three are from the oxide or the precious metal. Nickel, copper, zinc, lead, these are from base metals, etc. So, and I will later on explain why it's useful to organize them in this way. This is by when we are doing a process called IRR in CoDaPack. So once we have the data organized this way, you just copy it, you just paste it on a new table, and you save it as an XLS or as a CSV, not as a XLSS. CoDaPack sometimes opens, sometimes it cannot open XLSS. So it's easier to save it as XLS. So let's open CoDaPack. The first step will be to import the data. So you go to File, Import. As you see, you can import from R data if you have R, CSV or text, or XLX data. I will select XLX, and I will go to my folder, click Open. It will start reading from line number 1, which is the headers. If there are not available data, will be NA. We don't have not available data. We don't have below detection limit. We took care of all this. Just click OK. And here is your data already in CoDaPack. The first things that I would recommend you to do is to go to Statistics and select Atypicality Index. You select all the elements, click on the first one, Shift, click on the last one, select all the elements, and click Accept. And these are the 3 samples, the 11, 12, and 16. The 11, 9, 12, and the 16, which are atypical, which means they are completely different from the rest of the data set. This is usually samples that are related to mineralized areas. So I will usually take the coordinates of these 3 points and plot it on a map and see what it has. The program also created a new column here, which is called atypicality, which is, goes from 100% to 0%. Okay, so these 3 samples are samples that are above 95% significance. You can see this is 100%. Like the 11th sample is something that is really, really big. So the next step will be to convert our data to open data. it is closed now, as I explained before. To do that, you click on Data, Transformations, and you have three options to transform the data: the ILR, the CLR, and the ILR. So let's go with the first one, ALR. For that, again, you select all your data, click on the first one, click on the last one, Other, Shift click, select, and Accept. And the computer already creates all the ALR transformations. Do the same for CLR. In the case of CLR, the only difference is that you don't need to include the other. So just from molybdenum to phosphorus, shift click, select, and accept. And again, you will have the transformation for the CLR. Now, to do the transformation from the ILR, this is the most complex methods. Yes. So you go Data, Transform, go to ILR, select everything, including the other, Shift, and here to the right is where you define how you're going to arrange or group the elements for this analysis. And this goes back to the same table that I have here, the grouping elements. So we want to group by these elements here. So we go back to our table, and we need to define this matrix manually. So we define manually. And what we do now is we will select the elements that are on each group. So we know that for the first one, molybdenum, gold, and vanadium are part of one group. So I select the three. When I select the three, I click Next. And then I will select a combination of whatever combination, the first two or the last two, and then the other combination, because the only one that I am interested in is in the first one. Okay, so I will select, for example, this one and this one, click Next, and then this one and click Next. Now I'm ready to group the second group. So I will be interested in, when I get all my ILR, I will be interested in column 1, column 4, etc. So these are the elements for the base metals. So these 4, 1, 2, 3, 4, and then I will select, it doesn't matter which ones. I just need to select, to leave one unselected in order to finish the group. So the third group, which will be thallium and silver. These two is also base metal, but chalcophilic association. I select them. Next. I select any one of them. Next. The other group will be, so we are the chrome, manganese, barium. This is the lithophilic elements. Chrome, manganese, and barium. Chrome, manganese, barium. Click Next. Select, click Next. Select, click Next. And the last group will be the major elements. So I select them. One, two, three, 4, 5, 6. I do not select other. Next. Whatever. I just need to leave one unselected. Just to show you that you can can be whichever one, not selected, doesn't matter. And that's it. We have created our matrix. We click accept. You see the matrix here, and then we click accept. And now the computer generated also all the ELRs, but as I mentioned before, we are only interested in the first one, the fourth one, the seventh one, etc., the ones that correspond to the combination of these elements. So once you have the data in this way, you can just click File, export the data to an Excel, and we would call it this open data. And you can go back to Excel and continue working with your normal statistical parameters, etc. But since we are here, I want to show you a couple of things, how you can work within CoDaPack. I did put the result, all the results that you're going to see there in the original table. So the first thing that we're going to see is the variation array. In order to do that, CoDaPack, statistics, you have compositional statistics or classical statistics. Okay, you can do both. Compositional statistics, you select all the elements. You detect you want the center, which is the average, the percentile, the variation array, etc., etc. You can also include the percentile. You click accept, and here you get, let me put this bigger and this smaller. You get the variation array, and again, those elements in blue, in blue colors like this one are the less important, in red are the most important. So this is another way of reducing the amount of elements. You can see that there is a good, very strong correlation between sodium and potassium and gold, and aluminum and gold, and sodium and potassium and lead. So this matrix here is very useful, and you can copy, transfer it from Excel. You just select the all, press Ctrl+C to copy, and then you go back to your Coda and you just press the Ctrl+V and you get your data. Then I just deleted the lower part and I did conditional formatting, and I get the same distribution. I just put it here from red to green. You can use any conditional formatting that you want. The next step will be the CLR biplot, which is another way to determine which elements are the most important in your data set. So we go back to our CoDaPack, go to graphics, CLR biplot, and we select all the elements. We don't need to select other, Shift, select. And we don't have groups, okay, but if you have groups, you can add here, accept. And this is the graphic. In this case, you can add the observation name, I mean the name of the samples. So now you see the samples. You can zoom in, zoom out, change the orientation of the axis, increase the covariance, and of course you can take a snapshot and then go back to our Excel and just paste it. Now, the way to interpret this, just very quickly, the lines that are close to each other are repetitive. What you're looking for are elements that are completely opposite. For example, here we have silver and sodium and potassium that are completely opposite. That means that they can provide good interpretation.
So you look first for all the longest ones and the ones that are opposite to each other. So here's several combinations for this one and this one and this one, or this one and this one and this one. So you can select elements on different way. One of the way I do this, I just insert a circle and cover all the things so I can see which elements are above that circle, and it's easier to read. Let me show you quickly. Insert, shapes. I click Shift and I make my circles. If I click Shift, the circle will be perfectly centered. So I cover it and I see which elements are outside. Then I reduce, Shift again, Shift, reduce, and see which other elements now are important. So from this, we can determine that silver, nickel, manganese, barium, and sodium plus potassium manganese. These are two of the three ternary diagrams that will be very, very important. The next step is the principal component analysis. Very important method. So we go back, we can close this. So we go to statistics, to graphics, ternary analysis. So we said that it will be silver, sodium, potassium, and barium, I think it was. So this is the ternary diagram with the principal component analysis, and down here you get in the graph, in the body, you get the principal component analysis for that ternary diagram. You can also do the same thing for all the elements, and when you do that for all the elements, I just going to jump here. The only difference is that, as you can see, the principal component analysis, they give you the elements on the top and the principal component analysis as their rows and the elements of the column. So you need to copy this the same way. You select it all, you click Ctrl+C, but then when you're going to paste it on your Excel, you select Paste Transform, and you select it in this way. Now, once you have all the principal components selected, for example, what I do, I just go to the first one and I will arrange the data from the biggest to the smallest, and I will select, give them color to the two biggest one and the two smallest one, and that gives me a coefficient. And of course, this coefficient in this case is related to gold, so it's good. Gold by zinc divided by aluminum plus divided by the sum of sodium and potassium. This one here doing the same. We have silver and molybdenum down here, and barium and nickel up here. So this is probably more for the polymetallic one, etc. So how many of this? You see, we have 18, but we only use 7. Why? Because you take these numbers here, this is a cumulative explanation, and you create this table. And when the tables start getting flat, that it means that it doesn't add more information, you stop there. So in our case, it was the PC7 here with 96% explained, because after that, almost everything is the same. So the last step of working within CoDaPack will be the balanced dendrogram, and this is beautiful. It's a very powerful method. You again select all the elements, and here we should do again the definition of the matrix manually, repeating what we did. Just to save some time, I will use the default partition that most of the time it corresponds very well with the
one that we define manually. So if you are in a little bit of hurry or you don't know how exactly your elements, how to combine your elements exactly, go with the default partition. It will work perfectly well. And you get here your dendrogram. And in this dendrogram, you get basically 3 groups that you can see here: 1, 2, and 3. The explanation of how to interpret the dendrograms is beyond this video. I probably will have a specific video or a text to explain you how we do this. So again, you get the snapshot and you go back to your data and you click and that's it. You have it here. So this is basically the most important thing that you can do with CoDaPack. And right now you have your data already open. So what you do, you open file, open your open data. And you have here all the result. So I'm going to stop now to give you a chance to train with the thing. And on my next episode, I will show you how to arrange this data and how to continue processing the data using normal Excel. Today, we are going to finish the series on compositional data analysis. I will show you how to prepare the obtained data so you can work with Excel to do your normal processing. And also, because this will be very short, I will add as a bonus 2 applications that you can use to process really, really large data. And also, we're going to talk a little bit about dashboards in Excel. So, welcome again.
Once we finish processing our data with compositional data analysis package, the CoDaPack, and we export the data to Excel, we get this table here. The original values, the atypicality index, the ALR transformation, CLR transformation, and ILR transformation. So in this video, the first part, I'm going to be showing you how we're going to transform this file in order to use the normal statistical method that I described in previous videos. Let us start with the quick analysis atypicality, which is this one. And one of the things that we can do here, besides cutting and pasting here and having the coordinates, if you have the coordinates, just to plot these points on a map to see where are these atypicality data are located, you can just select the column, and when you browse at the bottom, you will see this, the quick analysis, and you click the quick analysis, and you can do like color, scales, data bars, totals, some charts, etc. But usually with the color, will show you immediately which are the samples that are very important, the green ones. So the next step will be to get your raw data, and to get your raw data is very simple. You just select all this data, and you just copy and paste, and you paste it in a new place. So there you have your raw data. Remember, as I mentioned before, you always keep your original data in a separate tab. Now, you do the same, you cut and paste all the ALR. And here, we also want to eliminate all this ALR dot and the dash other. To do that, just select that part, copy, right click and copy, and then go to Find and Select, Replace. Press Ctrl V here and replace with nothing. And it does all the replacement. Now get the other and the slash, right click, copy, come back here, Ctrl V, the same thing, replace all, and you have your data for the ILR ready to work. Same thing with the CLR. This is even simpler because you only have the CLR dot point. So select the CLR point, right click, copy, find and select, replace, Ctrl V, and replace all. And that's it. Now for the ILR, it's a little bit different because it's not that you're going to eliminate the ILR dot point because then you get just numbers. What you need to know is which of these numbers correspond to the association of elements that you did when you're doing the ILR matrix. Okay, and just to remind you, this is the matrix that you use during the processing of the data. And you can just right click in CoDaPack. You can select all this, click Ctrl C to copy, and then Ctrl V to paste here. And here you have the same data of the table, but in Excel, digital data. In order to select which columns you're going to be using, we're going to use a very simple formula. Here, we're going to test if the first value is equal to 1, then we leave it as 1. If not, we delete. We put nothing, blank. Once you do that, you copy and paste that to the whole table. And what you get here is a series of 1 values. And you will select for each suite, you will select the row that has all values equal to 1. So the oxidation suite will be the number 1, the base metal will be the number 4, the base metal calco file will be the number 8, etc. So now you come back here and you know that the number 1 will be the oxidation suite, which is usually the gold values. Then you go to number 4, which is base metals. Then we go to the next one, which is the 8, is base metal calco file. Next one will be the 10, which is the litho file. And the last one will be the major oxides, which is the 12. And we can eliminate the rest of the columns. So you get, I eliminate one extra, the number 10, sorry. Yeah, delete file. Sorry, I made a mistake there. So delete, these 3, these 2. So at the end, you will have a table with 5 columns, which are the oxidation suite, which is probably the precious metal, base metal calco file, litho file. That litho file and major oxide will probably be geologically related, although sometimes major oxide is related also to the alteration. So once you have your data in this way, you just export it to individual files and you continue the work with Excel. So this will be the end for the compositional data analysis, but since we have a little time, I'm gonna offer you as a bonus 2 more ways of processing the data with Excel, which are really, really interesting, and I hope you find it also very useful. You probably know that Excel can manage up to 48,000 rows of data. So what to do when you're dealing with files like satellite imagery, which has 2 million, 3 million points? Usually we use Surfer, and Surfer allows you to load as many points as you need. Like in this case, I loaded 3,299,287 rows of data, but you cannot do that in Excel, or can you? Let me show you how you can do this in Excel. So you start by clicking on data, and you can do this with loading the data from here, or just to get data from file from text CSV. And here I have this satellite imagery data that are 2 million, 3 million, 7 million points. So I'm going to use this one as an example. And here you have your data. Now, the next step, you're going to load not to the sheet, because you only can load here 1 million and something. You will click here and click on load to, and you will select only create a connection and add this data to the data model, and click OK. So here is the query, and here these are the rows that have been uploaded. So if you can see, we already passed the capacity of Excel, the normal capacity. Yeah, so we have the almost 3.3 million rows here. So the next step, we need to delete the lower values, the ones that doesn't have much information. Sometimes they are just noise. So in order to delete some of this value, you click here on the green icon, and it will open a separate window. On the separate window, here column 3 is the values that we are looking for. It can go from 1 up to 253. So let's say we're going to eliminate the first 100, 120 points. You click on the filter, you select number filters, greater than 120, you click OK. And now we only have 814,000 points, which is the file that we want. So we select the 3 columns, we click on copy, and depending on the speed of your computer, it will take several minutes to complete the copy of all these columns. So you go back to your spreadsheet and you click paste. I suggest you click paste spatial, and you select CSV and click OK. And again, in dependence on the speed of your computer, it will take sometimes several minutes to load the data. And when it's done, you're going to have file, which is the reduced file, which has only 800,000 rows of data. And that is how you can reduce the large data files that you receive from the satellite image or any huge data set. You just eliminate the lower values and you work with this part. Bonus number 2 will be dashboards. And these are instructions that you can do with Excel and allows you to interactively explore your data.
And this is an example of a dashboard which allows you to study two elements or a series of two elements in a scatter plot, and you can always change the elements, and when you change the elements it automatically upgrades the graphics, and you can select specific samples. For example, you want to select sample number 10 and it shows where it is, and it gives you here a description that cell 10 lags in both elements, which means this which is located in this quadrangle, and at the same time it gives you a graphic representation of the sample compared to the low, the middle, or the high point. And here you have a sample, a table that you can look around to see the other elements, and with the color scale it gives you where is the highest value for this element. So let's say we have molybdenum, so sample number 7 should have the molybdenum at one of the top, so here it is right at the top. So how do you get this? So you just have your data, and if you know Excel, you should know how to add more columns, etc. So you have your original data, you convert it to 100%, and then you work with this thing. Another example of a dashboard is this one, where I'm comparing different labs, different years, different geologists, different projects. And for example, you select the year 2018, and in 2019 there were only 2 labs, ACME and ACT. In 2019, let's try this one here. So we need to clean the thing to 1919, only 2 labs. So it's 217, the one that have the 3 labs. If I just want to see the heavy mineral concentrates, it gives me that information, the amount of sample, which geologist did it, the type of sample, the sample per lab, the spark lines, an interactive map of where the samples were sent. And this is a combination of things. You see how it immediately changed this thing. So this is a wonderful way of presenting your data to your boss or to your subordinates, just presenting your data. And the way you do this, you create the different types of graphics in individual tabs. So for example, this is the line pivot, the category pivot, the manage pivot, etc., etc. So in this case, the data is right here. And if this data, for example, is something that every month you get new data at the end of the month, you just need to add it down here, and it will upgrade all the graphics to this situation. So how do you construct this beauty? The easiest way for you is to look at this video. I will put a link in the webinar, and the file that was used during this presentation will be in Mendeley. I put all these Excel files, my Excel files, and the Excel files from the interactive Excel dashboard in Mendeley, so you can download it. The video is a little bit long, it's about an hour, but it is explaining you step by step how to build each of these pivot graphics. The other way that you can easily work with this is just adjust this table here, just add your number and use the dashboard that has already been made. This is something that will take you a little while, but you just do it once, and after that it's done. It's done for all the work that you have to do. So it's a very incredibly graphical way of presenting this data. And as always, remember to have a table of content at the beginning, so you can quickly jump to each of these tables.
Welcome back. So I hope this presentation show you the importance, actually the necessity of applying compositional data analysis when you are processing data, especially geochemical data. Please remember to subscribe, and until next Golden Drop episode, have a nice day.
My name is Ricardo Valls, and I am inviting all geology enthusiasts to discover a treasure trove of geological knowledge at my Valls Geoconsultant YouTube channel. As a professional geologist with over 41 years of international experience in the mining industry, I offer a wealth of high-quality, informative videos that bring the fascinating world of geology to life. From beginner-friendly explanations to in-depth explorations of complex concepts, I provide content for geologists of all levels. I cover a wide range of topics, including rock formations, plate tectonics, mineralogy, and even the application of artificial intelligence in geology. My clear, concise presentations make even the most challenging geological concepts accessible and enjoyable. Whether you're a student, professional geologist, or simply curious about Earth's processes, my channel is an invaluable resource. Don't miss this opportunity to enhance your geological understanding. Visit my Valls Geoconsultant channel today and subscribe to stay updated with my latest videos. Join our community of like-minded earth science enthusiasts. Your journey into the depths of geological exploration starts here.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe. And don't forget to click the notification bell.